Hello everybody. So, we shall conclude today with the design of slab bridge. Already we have done in detail for IRC 70R loading. Now, we shall take another problem on slab bridge only to give you idea. This is actually your lecture number 14 and that one we are considering here the same slab bridge, but we shall take a different problem we shall consider. And that one here. So, let us consider this one as a problem 2, and what we are doing here, just let me give you before coming to that I am telling you. So, this is your that slab cross section and we are having here the crash barrier and then footpath this one we are considering here, and for this we shall find out that we have changed the span. So, this one now coming to this one. So, let us see the clear span. So, same problem we are doing 10 meter, width of carriageway 7500 for double lane, width of the footpath we have taken it to 1500 millimeter on either side, width of crash barrier that means the bottom, that one we are having 450 millimeter, wearing coat 100 millimeter, IRC 70R loading. We have changed the grade of concrete that M30, steel AP 415, unit weight earlier we took it 24, now we have taken 25, wearing coat that is 22 kilonewton per meter cube. So, this is your the data whatever we are getting. Next we are considering that again clear depth we have taken, this is the one 12 we have taken. We can consider 13 also, we can consider 14 also, that also we can find out. On the basis of that we can find out the estimated depth and overall depth we are getting here. So, that means here what I have done basically here just I have added 833 millimeter and then added another 25 millimeter and rounded off. So, we are getting by 25 dividing. So, 850 millimeter we are getting here. Depth of the width of the bearing as usual we have taken 400 millimeters. So, effective span 10.4. So, we are getting this one 10.4. This is the one for solid slab we are considering here, and we would like to see that what is happening. It looks like the same problem, only the span is changed, and I have changed that unit weight of the concrete to 25, which is the usual case we should take it. So, as usual that Q slab for the dead weight. So, we are getting 21.25 kilonewton per meter square, and then wearing coat for the 2.2 and dead load we are getting 23.45 kilonewton per meter square. That I mean to say that per square meter you can get this much of load, it is coming here. So, we can find out that 317 it looks like quite high per meter width of slab we are getting here 23.45 and this particular one we are getting here. So, what we can do here that for the dead load shear force 23.45 into 10 to the power 0.4 to, so 121.94 kilonewton meter. So, that we can get it per meter width of the slab. So, we have got that one as usual, we can get that for the bending moment and for the shear force that we can find out, and that is coming here in this particular one we can get it here. The next question is coming into picture. This part there is no problem because we are going from the top of the wearing coat to the bottom one, that on the top of concrete. So, that one we shall get the same one we are getting for IRC loading, that we can get it. And as usual that B, now it will be changed. B means total B. Now we are considering here, just to give you idea, that one we are talking this one as our B we are considering here. Okay. So, sorry. So, this one we are considering here, that B we can get it here, and then this is our depth D. So, crash barrier generally as per IRC 5 we can get this one, we take 450, this one also 450. So, what we can do it here, we can find out now that your B, total B, which is coming as 11.4 meter, and B by L 1.096. So, we can get the alpha value which is coming, this particular one we can get it here, that alpha value we can get it, that 2.595, that we can get it from the table, that we can find out. Effective depth, again we can calculate that one on the basis of that AL, AX, because we are considering at the middle, the load is given at the middle. So, in B, so we are getting here the same value, we will get it here, there will be no change here. Only thing, because that B, that other things, that X value because of this one will be changed, and AL also. So, we have got this particular here 7.788 meter, that effective depth for a single load, that means for the one track, that we are getting 7.788 meter. So, you can compare that one, earlier one, you can compare, and you can see that how much is the difference we are getting here. So, coming to this particular one here, center of left track, the vehicle is here. So, let me give you the vehicle. The vehicle is here. So, this is our left track, and from the left track we can get the central line of that. So, we can find out from here to here, we can find out, from here to here we can find out, that means other way also can find out. So, that from there we can get that how much this length will come, that we can find out. This particular one we can find out here, that is the one we are doing, this particular one here. So, whatever we can do it here, the center of left track from the left end of bridge. So, 0.45, that is the crash barrier, plus 1.5, that is the footpath. Then we are having that between the end of footpath to the outer of the track, and then the center line of the track, which is coming where 3.57. Half of the effective width of the dispersion, because already I have got 7.788. So, which is coming as 3.894. So, that means this 3.894 we are getting it here. So, obviously, we have to go up to this. So, 3.57 we have got it here. Next one, right part, again we shall do it. So, 0.45. So, this particular one we are getting from the right wheel from the left end of bridge 5.63, and the width of the bridge, that B 11.4 minus 5. So, that means from the right side we are getting 5.7, from right end we are getting 5.77. So, it is coming 3.894, that is less than this. So, that means I can take the full dispersion on the right side 3.894, we can take it, and which we have taken this value, that we can get it. So, which is we are getting here 9.524, that effective width that we are getting for the, this is for the bending moment, because the for bending moment, that as we have told earlier, that we have kept that load at the middle, and on the basis of that we have got this value. So, effective length you can again find out, which is coming as 6.47, that particular one we are getting, that as similar fashion whatever we are getting. So, this is for the shear force, the same value we will get for shear force also, 6.47 meter we shall get it here, that we can find out, and then we can do this particular one problem. So, again the same way we have got it for the shear force also. same way, the same fashion we are getting this one also, that your dispersion, that 5.81 meter we have got it for single load, and then similar fashion we have got it for the both the track for the full vehicle we have to consider, and which we can find out here, the 3.57 and 2.905. So, we can take this particular one here, that we can find out. So, then we can find out this one, similarly for the right part also we can find out, and then we are getting that effective depth with that one we are getting 7.87, that one we are getting it here. So, we can find out this one, we can find out, because why I am showing you this particular similar problem, because we would like to see that one, that what happens actually with that increasing that slab, because otherwise one can say that why shall we go for other type of bridge, only we can go for actually this all can be slab only, that is the one. So, this problem I would like to show that one, that whether really that all bridges can be made by slab bridge only. Definitely that since there are so many bridges, so it means that we require that other type of bridges also. Coming to this one here, I can say again, already we have discussed all those things, because just I have repeated, because this particular one made through computer program, that is why it has come. Again we are giving this particular one here, so that you can immediately you can find out that whether that proper value is. So, here for spans of 9 meter or more, for tracked vehicles 10% up to span of 40 meter, that means it will be 10% here. So, these are the cases. So, this particular one you can get it for all RCC one, this is sufficient for the impact one, you can get it. So, on the basis of that, immediately you can find out for RCC bridges of 10.4 meter and class IRC 70 at tracked loading, we are getting impact percentage 10, and so impact factor we are getting here 1.1. So, we can find out the intensity of loading, which is coming very less, because he would say that dispersion width actually more. So, we can find out 12.496, maximum live load bending moment 12.496 into 6.47 by 2 into 10.4. This one in the last one possibly that there is a certain kind of that value, it will change little bit, that you please check that one. I shall give it on the slide, the corrected one you will find out, and that you can compare. Design bending moment here, which I mean to say this particular one, these are the two values you are getting. So, you can imagine whenever you are considering that dead load and live load, the objective is that our objective for bridge design or provide the proper bridge, that there is something that in structural design also you can say that your live load is your requirement. That means, the vehicles to be passed in this case over the bridge, that one we have to consider here. Now, considering that aspect, whenever the vehicles moving, because of that whatever bending moment you are getting, and to take care that load you are giving actually more, that you have to supporting system actually require more bending moment. So, that is not at all say desirable. Say for example, if you consider the dead load plus live load, if you consider this one as a 100%, so obviously you can consider that if dead load is less than 50%, that due to bending moment due to dead load is less than 50%, then we can say that is optimized. Anyway, for argument's sake, that is not possible that to get say less than 50% bending moment. I mean to say that let us say 40 you are getting for dead load and 60 you are getting for live load. That means, you can take care that your say supporting system can is light, that we can say. For argument's sake, okay, that may be difficult. So, let us say 50-50, that is also quite acceptable. But if we go towards more, that means sometimes 60% actually your dead load and live load is actually say 40%, and long span one you can find out that one also further actually, that for the dead load it will be further actually for bending moment due to dead load will be further more compared to the live load of the due to vehicle, that way. So, here you can imagine that particular one almost it is more than 50%, 1/3, 2/3 in that particular way we can get it. That means, we have to find out the section for this. This is actually, this is our requirement, but this one to get this one, to achieve this one we have to provide this much of bending moment, then only we can achieve. That is the one of what I would like to say, that why we should go for actually new one, the other one we shall go, that we can find out here. So, this is the that bending moment, that way you can consider here. Similarly, we can find out that your say for shear force due to live load, that we can find out here, dead load and live load. So, total we are getting 189. So, we have to check this one with that particular section. So, now we have to design, we have taken working stress method, but I shall give you other problems also, that one we shall give you for limit state other problems. That same problem we shall do it, but just we shall finish that one for RCC T-beam also, and then we shall give that problem, as well as we shall give that one the solution also. We shall give so that you can also go through it also, that whole thing we can go through, other than your video, that we can do it. So, this problem we shall do it by because first we are doing working stress method, that is the starting point, because if you do not, if you just only use one method, then obviously you cannot compare. So, here whatever we are doing here 850 25. So, this particular one we can find out, and that we can solve this problem, and then we are getting here 807.5 850 plus minus 32, and KB we have got this one, JB also we have got the similar fashion, the same slide, almost similar slide you can find out there also, and that you can find out, and then half sigma CBC KB JB B D square. So, we can get this particular bending moment, that you can find out here. So, this is the one we can find out, that 9. So, 954 and requirement is 461. So, that one now whether we shall, as I have told earlier also, that this value, that is very important. This is the resistance due to concrete, and that one should be more, because we do not want that concrete will fail fast. That is the thing that we do not want. So, effective depth provided this one, and this is the one, that compressive force, and on the basis of that we can find out that balanced area of steel, that is 6991.2. That means, this one also will resist this much of bending moment, but our requirement is very less, 461. So, we shall provide near, on the basis of that we shall provide. So, we can find out this one here, on the basis of that we require only 3382, and which is coming, actually we are providing 4908. That means, we are actually in between. That is the thing I would like to say, and that I am going to actually emphasize that one, that how to design that particular one, that one you have to consider here. So, coming to this one here, just let me give you this particular one problem. What actually we are doing, the basic philosophy, that what we are doing basically here, that if we consider that, let us consider any arbitrary section, okay, just consider say rectangular section only, and it has a, for this case we have solved this problem. And we have a lever arm. This is D. And this one X. So, X equal to K D, then we can find out here Then we can find out here x equal to, we can say kd. This is your C and this is your T. So, what we can do, that m equal to Cz equal to Tz. This one we do not know how much it is. So, what we shall say, again I am telling this one say T, again I am telling this one say C, this one again for this case also D, this is your x, and this one we call it as K2. So, what I mean to say that whenever you are solving this problem here, then we are giving a specific values j that equal to 1 minus k by 3, all those things you write down. This is our z. So, our objective here in general, whatever we can consider here, again m equal to say Cz, that is your say, again we are telling say Tz. For this case, that is the one which we have told you from this particular one here, and this one also the same thing it represents. And then we can say C equal to Q1 FCK BD, that particular one we can consider here. Similarly, we can say Z equal to D minus K2x equal to 1, this particular one, minus K2 into K D, because K equal to x by D. So, that means here whatever we are talking, this one here x, this particular one here, the same way we can represent. The what I mean to say that whether you work with the working stress method, whether you work with the limit state method, that these values are only going to change, but basic equation remains same. That is what actually we consider here, that basic equation actually remains same. So, coming to this particular one here, we can find out on the basis of that we can find out the solution, and which will be again, say for example, for this case whenever we are talking this one say m equal to, we consider say 0.87 Fy Ast then Jd. So, this one we can write down here Jd. So, then what I can say that m equal to K3 say Fy Ast Jd. This K3 means whatever the value we can consider. That means, I can always say that parameter I can say, and on the basis of that we can actually find out, and on the basis of that we can solve. That means, your main thing that here I mean to say that FCK and your Fy, as I have told you earlier, that m equal to 280 by 3 sigma CBC, and as we all know, sigma CBC is nothing but FCK by 3, this is the one we get it. So, that means, we can say m equal to 280 by 3 into FCK by 3, which comes as 280 by 3 only. So, sorry, FCK. So, that means here we can write down this parameter in terms of FCK that we can write down 280. So, that means here what I mean to say, we can write down all of them in terms of FCK and Fy, and on the basis of that we can solve. So, in general that you are having only two equations, one is called that equilibrium equation and the other one is the moment equation. And these two equations, that means one for the M say C for concrete, another one we shall get it for concrete, let us write down, and this is for steel. So, we can write down this one, we can do it, and on the basis of that we can find. This is our whole objective that I am trying to say, that I shall give you one problem with that one we shall give you, because then it will be easier to know that one, that how much is the difference we are getting. Another one important factor, that is your say partial safety factor, that is also there, and that partial safety factor will be that with the different kind of loading, other things, that one also we shall give, and that one we shall take it with that IRC 112, that we can consider, that we shall do it here. So, this is the thing we do it here. Coming to this particular one here, we have got this 3382.4, that is our requirement, and then we are providing 25 millimeter. So, this one we are providing here, and so we can get 25 millimeter die at 100 millimeter center to center. So, for now the thing is that why we shall go for it, I have told earlier also, once more let me repeat that we would like to make this one here, the whatever moment is required, then concrete should be at the top. This is the resistance by concrete, this is your say applied moment, and steel will come here. So, this one the steel will come here, so that we can find out this one in between. So, we can always give guarantee that it is actually becoming under reinforced. So, this is the one we are getting it here. So, let us see that how much we are getting due to your say shear force. So, I have taken this one M30. So, steel grade is Fe409, that one we have considered, and so we are getting D, which equal to 850, that particular one we are getting 807.5 millimeter, that way we have already calculated, and so which is coming very less. So, that means here no reinforcement required, and for shear, however, we provide certain reinforcement to hold that your say top bars, that also we do it, and that one will give you the nominal reinforcement if you require that one as per the codal provision, that also we can do it. So, this is the whole thing we can do it. Now, we shall give you problem on this remaining one, we shall give that different problems we shall give you, and that so that you can understand that, because whatever we are giving that one with the limited time, only we are considering that your that main criteria we are going to. So, we can compare that, and also that I have not given you say IRC class A loading also, and IRC 70 or wheel loading also, that also we shall consider, and that we shall take care in your say RCC T beam, that one we shall do it. And one more thing that we shall consider, that one also your say abutment also, that one at least I should introduce that one also. So, with this we shall conclude that one, say your design of that slab bridge, which is very common. And this last problem I have shown you that one just to give you idea that why we restrict ourselves that one with a certain span, and that one we can consider here, that I can say that again I am telling this particular here, we have taken that one, if this is your zeros span, and so we are going here up to say 10 meter, and then another one we are getting it here say 20 meter. That means here our boundary we can go little bit more, let us say maximum say something say 25 meter. That is our scope of this the course that we shall go. That means initially we have started with say 5 meter, then we have gone to that one say 10 meter, then we shall approach towards 20 meter, and mainly we have considered that one your say superstructure. Now, we shall consider that one say superstructure we have considered, and then we shall go for it actually here another one that you would say how shall we do the abutment. So, let us conclude with this one with the design of slab. We shall come in detail in other part also we shall come. Thank you very much.